Welcome to the first recorded lecture in a sequence of lectures that I'm presenting on undergraduate analysis. These are not meant to be comprehensive, but to just give students the highlights. So if you're learning this for the first time, it helps get you perspective on the material that you're going to be seeing in class, helps with reading the book. If you've seen the material before, it can just be used as a nice refresher, kind of shake the rust off of some ideas that maybe you haven't visited for a while. So the material that I'm going to be presenting starts in chapter 2 of the Kenneth Ross book on elementary analysis. I will begin with sequences and proofs and how to read mathematical definitions and formulate a strategy for writing a proof from the definition. The material in this recorded lecture covers sections 7 and 8 of Ross. Those are the first two sections of chapter 2. The first chapter of Ross just deals with the construction of the real number line somewhat and properties of real numbers and sets of real numbers. It's very important. You should read it. It also talks about the principle for proofs by induction, very important topics, but it's often material people have picked up along the way in a lot of other courses. So I think, the meat of the book really starts in chapter 2, and I'm going to present a series of recorded lectures over the remaining chapters of that book on elementary analysis by Kenneth Ross. So without further ado, I'm going to jump right into it. The definition that we begin with is of a sequence, which I always show like in italics here, sequence, and it's a function whose domain, all right, so this is really important perspective on sequences. Sequences are functions. So functions have domains and ranges. What's the domain of a sequence? A domain of the sequence is a subset of the integers, right? That's what this symbol with this kind of fancy Z that you might draw like that if you were to try to do it by hand. You'll see that below. And it's of the form all the integers that are greater than or equal to some initial one. Now, the integers can be negative, right? Like -10 is an integer. So you might start your sequence at -10. That would be the first term. Might seem a little odd to do that, but maybe you have good reason to. Then the second term would have to be -9, -8 would be the third term, and so on. Typically, the m, the little m we use, this fixed one that we have for whatever sequence, is typically 1. Sometimes we'll let it be 0. Those are the most common choices, but sometimes there's good reason to choose others. So a lot of times we'll actually just choose our indices to be the natural numbers, which is this kind of funny looking n I just drew on the screen right here. Those are the numbers, that's the set. Put it in curly brackets when I talk about a set of numbers 1, 2, 3, 4, and so on. You get the idea of what those are. That's how you define the natural numbers, the whole numbers, the counting numbers. That's what they're usually called. But anyways, sequence is a function whose domain is some subset of Z where it's kind of all the integers after some initial fixed specified integer. And then the sequence, which is a function, takes that integer and it maps it to some value in a range. All right, for all the integers in its domain. And that range could be just about anything. And in an undergraduate analysis course, you'll see that we'll often consider sequences of real numbers, but we'll also consider sequences of functions. In more advanced analysis classes, you could consider sequences of operators. But you could have sequences of geometric objects, like a sequence of different types of squares and circles and ellipses, and you could mix them all up and have a sequence. So it doesn't really matter, but for focus and for our purposes, we're going to focus on sequences of real numbers. Now, it's necessary to introduce some notation for this. We will either use parentheses or curly brackets with a subscript of n equals m and a superscript to infinity, just to denote that that's all these points that go from, integer m up to infinity, right? There's all the ones above m. When m is clear from context, or we just kind of expect that it's equal to 1 as the default, then we'll often drop the subscript and the superscript and just use parentheses for a sequence, sometimes the set. Now, it depends on the text. The older text that you look at and older references, they'll typically use curly brackets. Newer texts on analysis, they often use parentheses. There's been some sort of shift in the community over time. I prefer to use parentheses. Ross uses parentheses, so that's why I underlined it here. That's going to be the notation I typically use. And then when I want to consider the sequence, instead of as an ordered set of numbers, I'll drop the parentheses and I'll use curly brackets. That's kind of a standard thing. So you stop. Sometimes you think of the sequence as a set of ordered numbers, and other times you just think of it as a set of numbers, and the ordering doesn't matter. Okay. So it depends on the context. It's usually pretty clear. If it's a little confusing, it gets better with practice. So I've emphasized this above, but this statement it really needs to be hammered home. Think of this notation S sub n is as the functional notation. And if you see subscripts in analysis, you should think of it as S of n, right? S sub n is S of n. And that holds pretty universally throughout most of analysis, is that subscripts are denoting some sort of dependence on whatever we're putting in the subscript. So that's, I think, a very useful way to think of it. And then you can think of how to plot a sequence if you're given it. So for example, what I'm showing here is if I tell you that the first 4 terms in the sequence Sn here are 1, so that's S sub 1, 3, which is S sub 2, 2, which is S sub 3, and 1.5, which is, excuse me, I made a little mistake there, S sub 4, then I think of this as S of 1, S of 2, S of 3, and S of 4. And so then when I look at the plot, I say, hey, S sub 1, it's S is the function that takes the value 1, and what does it do? Oh, it gives the value 1 back. And then S sub 2 is really S of 2. It takes the value 2, and oh, what does it do? It gives the value 3, right? And then S sub 3, S of 3, it takes the value 3, and this time it gives the value 2 back. And S sub 4 takes the value 4, and it gives the value actually 1.5. So now it's not an integer at all. That's about right here, right? And which is plotted here, which I just circled. So hopefully that kind of clears some things up for you. I'm going to erase some of that just to declutter the screen, because I'll be giving these OneNotes that I'm preparing these recorded lectures in. They'll be given with the recorded lectures along with the typed lecture note material that accompanies the Kenneth Ross book on the various chapters that will also accompany these recorded lectures. And that's where I've actually these typed definitions and theorems material that looks typed like this definition 2 below. That's all from these typed lecture notes. If you're wondering where I got that from, there's PDFs for that that are also provided. So, all right, let's look at what it means for a sequence to converge. A sequence S sub n of real numbers is said to converge. So in italics, I'm defining what I mean for convert, or what the property is that I'm defining is always in italics. If there exists a real number S such that for every epsilon greater than 0, so that's 1 underline, it just spans 2 lines, there exists a real number n, terrible underline there, there's a better one, such that for every or for all integers little n greater than or equal to capital N, the conclusion is we will have that S sub n minus S in absolute value, or the distance between Sn and S is less than epsilon. So what did I just do? I'm underlining all the logical things, the logical quantifiers that you have to address when you're going to do a proof by definition. So mathematical definitions are very precise, and you need to be on the lookout for the words there exist, for every, for all, there is. These are all the terms, the logical terms, and they need to be addressed in the order in which they're given when you use the definition to prove something. So the first thing you ever need to do if you're saying, I'm given a sequence Sn and I want to prove it converges, is you need to show that there exists a number S. Now, sometimes you're told what that number could be. So that might be optional. This might be given, this first thing right here, S, but it might not. So it depends on the problem whether or not you have to do that. So I'm going to number the steps you have here, but I'm going to number this step as 0 just to emphasize that sometimes you don't have to do that. Sometimes it's given to you as the statement of the problem, or you can assume it exists by this somehow the way the problem is phrased. You'll see an example of this below. So what you cannot skip is for every epsilon greater than 0, there exists an n such that for all integers little n greater than or equal to that capital N, the conclusion follows, right? So there's nominally 5 steps, but if the limit is specified as the statement of the problem, there would only be 4 steps. You can never get a proof by definition for a sequence converging in less than 4 steps. And this gives you the outline, the structure of the proof, the exact order in which you must address things. Now, formally, this number S that we're talking about in definition 3, we define this as the limit of the sequence if we have a convergent sequence that converges to this number s. And there's lots of ways in which you can denote the limit. You could say, this limit sub n goes to infinity of s sub n is equal to s, or just drop it. It's implied what you're taking the limit of in that notation, or this notation, s sub n with an arrow or right arrow to s. That's actually my preferred notation because I'm lazy. So it's the easiest thing for me to write. Ross does that a lot. It's a pretty common notation. There's other notations. Usually it's pretty clear what's meant by the, a sequence converging to a number s, and that number s being the limit. So in pictures, right, if I say that I wanted to graphically look at what does it mean for sequence Sn to converge to a number s, here's a graphical interpretation of this. Here is some sequence that I drew that's converging to this number s here. So the s is supposed to be the limit. And what that means, okay, is that for any epsilon greater than 0, so I've established s there, so now I move on. For any number epsilon greater than 0, pick a number epsilon, any number, as long as it's greater than 0, there is some index that I may be able to go out, or that I have to be able to go out far enough in the sequence such that that term and all the terms that follow that term in the sequence are within an epsilon distance of the number s. And I've indicated that interval then around s, where all the terms in the sequence have to be, by these dashed horizontal red lines. All right. So epsilon is like an error tolerance. You're saying, I don't ever require my sequence to become just equal to the limit, but it needs to be able to get arbitrarily close as I need it to be for any epsilon I choose. But the idea is when you prove something is you first start saying, I pick this epsilon greater than 0. And then someone says, I choose a capital N that depends on that epsilon. So you might sometimes see that the n is written as n sub epsilon to indicate, again, a functional dependence. You really mean capital N of epsilon. Because if I chose a smaller epsilon, you might see this from the graph. Imagine I picked epsilon to be half the epsilon I graphed. The n that I chose here would no longer work. I'd have to go out probably to at least n plus 3, because s sub n plus 2 is about the same value as s sub n. And those looks like greater than whatever the epsilon over 2 value is for the given epsilon I've picked here, right? If I divided that epsilon value in half. So something to consider, and that's kind of just the long and short of it in graphical form. You could pick it apart. You might want to plot different kind of convergent sequences if you have ideas of different sequences that converge, and play around with different epsilon values and see how far out you have to go. But I think some of the examples that we're going to show will drive this point home. Now, we're going to go to writing things with symbols. We'll move up the screen here. Sorry about that. And we'll use upside down capital A's to mean for all, for every, for each, for any, any logical equivalent to pick one, anyone, maybe subject to some condition, like for any epsilon that's greater than 0. And then the backwards capital E will be for logical terms, there exists, there is. So for those types of quantifiers in your definitions, you'll use this backwards capital E. Now, I write this to make a point. It really emphasizes, I think, in a person's mind when you're learning mathematics and analysis, where the work is. It's easier to identify in the definition when it's written in symbols, because we just look for these symbols. And the thing to keep in mind is when you are writing a proof from a definition, if you ever are coming to the step, again, I numbered these things saying these are the steps. The there exist steps are where kind of all the work is. Those are usually representing the hard parts. The for every are easy, because all you have to do is pick one, anyone, as long as it's subject to some condition. Like for every epsilon greater than 0, you're going to say, hey, let epsilon be greater than 0, which means to the reader that when you write the proof, pick an epsilon, any epsilon, I don't care. It just has to be greater than 0, but fix it. But then that's the value. Then I have to somehow say that there exists a capital N. That's going to probably be some work. Like, how do I know that there exists a capital N? You're going to have to do some scratch work, some investigative work. Then you have for any integer, little n greater than or equal to capital N, you say, well, let little n be greater than or equal to capital N. Pick a little n, any n, as long as it's greater than or equal to capital N. Those are such easy things to write in proofs. It's the conclusions, it's the there exists. That's where the work is. So, all right, the shorthand definition in symbols is a sequence Sn of real numbers. This symbol right here is like a C that's kind of midway up the line. and it's for like contained in. So S sub n is a subset contained in the reals. It's a set, it's a sequence of real numbers, and it converges if there exists, right? I'll label things as before, this real number S such that for every epsilon greater than 0, there exists some number n, right? So it's implied that n is like a number here, such that for all little n greater than or equal to capital N, that are of course the indices, like integers, S sub n minus S, an absolute value, this is our conclusion, so I'll double underline it, is less than epsilon. So just again, writing this out more top down, when we're proving a sequence of real numbers converge, the sometimes optional step is step 0. We have to show that there exists a real number S. And you have to say, how do I show something exists? Well, if it's given to me, I don't have to show anything, right? So then I'd skip this step. But let's say it wasn't. Then there's kind of two ways that you could show something exists. You could either give one up, say, well, the limit is 7. The limit is pi. You know, like you just say, this is what it is. Just serve it up. Or you can explain how to construct one. You could give a recipe, if you will, for these are the steps you follow, and you would construct the object, this limit, this S, that has the desired property we want, that it is the limit. Once you've done that, you know, if you have to do that step, that is, you go on to say, oh, what's the first thing I have to address? The always, and I can never skip in this definition, is for all epsilon greater than 0. That implies, what do I write in my proof? There's a lot of standard ways to write this. The shortest one is let epsilon be greater than 0. In kind of mathematical notation, it's this: let epsilon be greater than 0. That's how you read that. So that's a complete sentence. You read it in English, you write it this way: let epsilon be greater than 0. So what you're saying to the reader is, pick an epsilon, any epsilon, it just has to be greater than 0. You could also say, consider any epsilon greater than 0. Again, the idea is you pick it and it's fixed. Now you might say, well, I'm not happy with the one you pick. I want to pick a smaller one. That's fine. Pick a smaller one. But then once you've picked that, I will pick an n that maybe depends on epsilon. It might be a function of epsilon. All right. I have to show that. How do I show that there exists an n that might depend on epsilon? Again, I either give the n or explain how to construct one. And again, it probably depends on epsilon. In the most general cases, it's going to. Then I have this part of the proof for all little n greater than or equal to capital N. Again, I would just write let little n be greater than or equal to capital N, which means pick a little n, any n, as long as it's greater than or equal to capital N. And then what am I going to show? I am going to show the conclusion holds, which is my fourth step. That for all such little n's, everything I've done before in this proof, that has now given me the conclusion I want, that the absolute value of Sn minus S, also read as the distance between Sn and S, is less than epsilon. So let's see this in action. Here is an example that proves that 1 over n converges. Notice, I just say prove it converges. I don't say prove it converges to what. So the first thing I have to do, I cannot skip. This is not optional here. I have to provide some candidate for the limit, S. So I'm just going to state to the reader, we will prove that 1 over n converges to 0, right? That's how you read that statement in English. Now I say, let epsilon be greater than 0. There's my first step. Now I have to say, how do I choose a capital N? How do I show that there exists a capital N that might depend on epsilon, so that I make sure all my terms in the sequence starting at that capital N and beyond are within the proper distance of epsilon? Well, it's pretty easy to see, because my sequence is 1 over n, that if I choose capital N to be greater than 1 over epsilon, then 1 over capital N will be less than epsilon. And I note that this is optional to say this additional part of this sentence, so 1 over n is less than epsilon. But what you're doing is setting up the reader for a great deal of clarity. When they read through the conclusion, they go, oh, I see exactly why you chose that capital N the way you did. So you don't have to. I think it's pretty clear if you don't say that, but you have to think of, if you hand your proof off to a fellow classmate, somebody else that's reviewing your work, you want your work to be as clear as possible. You don't want it to maybe seem like it's a well-motivated choice for these terms. You want to show that there's maybe some thought that was put into it. Not always. It depends on who your audience is as well. All right. So our third step, for all little n greater than or equal to capital N, well, guess what we write? let little n be greater than or equal to capital N. Again, what does that mean? Pick a little n, any n, as long as it's greater than or equal to this capital N. And then I just go through the algebra. I need to show that the distance between Sn and S is less than epsilon. Well, my Sn is 1 over n, and my S is 0. And I have to show the absolute value of the distance between those things is less than epsilon. Well, absolute value of 1 over n is just 1 over n, because I'm assuming that these are positive, right? Without the indices on this sequence here, I'm just assuming that it's from 1 to infinity. All right? Should hopefully be clear that that's the intention here. Well, 1 over little n is less than or equal to 1 over capital N if little n is greater than or equal to capital N. That's pretty obvious. You can just, if you're just dividing by positive numbers, divide by little n and divide by capital N, and you see that inequality immediately. And our optional thing that we wrote here now makes this final inequality completely clear. 1 over capital N is strictly less than epsilon. So there you have it. By this you go through this sequence of results, you work yourself top down here, and you say, hey, this difference here is equal to 1 over n, which was less than or equal to 1 over capital N, which was strictly less than epsilon. So this is less than epsilon. And that's it. That's exactly what you have to show. So your proof is done. So I draw like a box to indicate the proof is done. Some people will write QED. That does not mean quite easily done, but it is a Latin term that essentially translates to as was to be shown. There's other ways that you can use it. Probably the least pretentious way that you could end a proof is just draw a box to kind of indicate this is done. Moving on. So let's move on ourselves. Let's move on to this sequence. Prove that 3n plus 5 over 7n minus 6 converges to 3/7. Now here, the limit is given, which means that step 0 can be skipped. So we hopefully very clear why I labeled it as step 0. Sometimes I have to do it, sometimes I don't. Now, before we dive into the proof, we say this is a little bit harder of a sequence to work with, or it's not as clear maybe what the capital N should be. So we know that our goal ultimately is to construct this capital N such that when the little n is chosen in capital greater than or equal to capital N, then the distance between Sn, which is 3n plus 5 divided by 7n minus 6, and its limit, which we're told is 3/7, has to be less than epsilon. So you do a little scratch work and say, well, what does it look like? What does the sequence look like, this difference of terms for this little n? So you go through some algebra. You might pause the recording and look at the step. I'm not going to spend any time really discussing it. It's algebra. You go through it. What do you see? You see that this difference, you can drop some absolute values and you get 53 over the product of 7 and 7n minus 6 in the denominator. And what do you need? You need that ratio is less than epsilon, right? That's what you're after. So you just do algebra now. You just solve for little n in terms of epsilon. And then you see this inequality, what I need is true if little n is greater than 53 over 7 epsilon plus 6. Well, that means if I choose capital N to be greater than 53 over 7 epsilon plus 6, then for little n greater than or equal to capital N, this inequality will be true. So that's what I needed to do. That's my scratch work. Now, you don't present it that way when you write your proof. It will look far more elegant, as you're about to see. And people will just be like, wow. They're like, wow, how did you know to choose that capital N? Here's insight, but there is some work that was done for this. So let's just write it out. We skip our step 0, but we can never skip our step 1. Let epsilon be greater than 0. Again, pick an epsilon, any epsilon, as long as it's greater than 0. And now we say choose our capital N greater than what we know from our scratch work, 53 over 7 epsilon plus 6. Now notice I say, hey, that implies that epsilon is greater than 53 over 7 times 7 capital N minus 6, which it's pretty easy to see that by just remanipulating this step up here that I'm drawing some squiggly underlines on, and I'll erase them to clean it up. If you wanted to show you more work about that, you could, but the idea is kind of just setting the reader up. It's optional, but you want to set them up for the kind of final step or final part of step 4, the conclusion. So we get to step 3. Again, it's easy. Let little n be greater than or equal to capital N. Easy part of the proof. Pick a little n, any n, as long as it's greater than or equal to capital N. And then what do we know? We know through some algebra, but step 4, you can maybe pause and look. but we get very clearly, maybe skip a little bit of algebraic steps, that now we have that our Sn and S, the distance between them is strictly less than epsilon. So we are done. That is the end of our proof. We draw our box and we move on. You might want to rewind or just pause the proof, look it over. You might even just want to try it on your own. Just put the screen aside and see if you come up with the same thing. Okay, moving on. Now, we've talked so far just about what it means for a sequence of real numbers to converge, but we haven't said what it means to diverge. So what's very common in mathematical text is we just say, hey, if a sequence doesn't have this property, then we define that as something else, like divergence, which is very concise. Mathematicians love to do this. If a sequence doesn't converge, then it diverges. But then that doesn't really help you with the proof of what does it mean for a sequence to diverge. So if something doesn't have a property that has a mathematically precise definition, you just go through and logically do a logical negation of the definition. You might want to go review Wikipedia article on logical quantifiers and some basic logic if you haven't seen this or you've forgotten some basic stuff about proof writing. The take-home message is, wherever there was a for all, it becomes a there exist. Wherever there was a there exist, there's a for all. And the only inequalities that you'll ever change are ones that are conclusions. All right, they're not conditions on terms that you have. It's on the conclusion that you have. So I wrote it in symbols here, but I'm going to scroll back up and show the definition of convergence in symbols, the shorthand definition right here on the screen. And we see that, hey, a sequence Sn of real numbers converges if there exists an S, which means that we're going to say a sequence Sn diverges if for every S, right? There is no limit. Or there is no real number, I should say, that is the limit. We will have divergence with a limit existing when we talk about divergence to plus or minus infinity. But without that, we'll talk about a sequence diverges if for every real number S, there exists an epsilon greater than 0, such that for every capital N, there exists a little n greater than or equal to capital N, such that the distance between Sn and S is greater than or equal to epsilon. That will be the logical negation. And if that's very confusing to you, I think you need to go review some logical quantifiers, and this material is online. There's lots of resources for that, but just look at, logical quantifier, logical negation, play around with some of that, and go through some resources online if you need review. In symbols, again, I'm just summarizing right here on the screen what I said above. A sequence of real numbers S diverges, that's our definition, if for every real number S, there exists an epsilon greater than 0, such that for all capital N, there exists a little n greater than or equal to capital N, such that the absolute value of Sn minus S is greater than or equal to epsilon. All right, the distance between Sn and S is greater than or equal to epsilon. So now I labeled these steps 1 through 5, and it's because that first step you can't skip. You can't. Whereas sometimes you could say, hey, if the limit's given to me, I could skip it. But here you can't. You have to say, hey, pick a real number S, whatever number you want to pick. I don't care what it is, and I'm going to explain how I can show that I can always go far out in the sequence, as far as I need to, and find a term in that sequence that's beyond a distance of a positive, this positive epsilon. Like I could fix an epsilon greater than 0 and always go far enough out. There's an infinite number of terms essentially that are farther away from S than this distance of epsilon. So as an example of this, let's prove that -1 to the n as a sequence diverges. Some scratch work. Look at the plot of this. It bounces back and forth between -1 and 1. Even terms are at 1, odd terms are at -1. Now, if you were to try to prove that this converged, what you might do, and this is something you'll see in a future lecture in about 2 lectures from now, is you might consider subsequences. Because it's not clear. This is a sequence that's jumping around. And if you had a sequence that was maybe bouncing around, but maybe the terms were getting closer together, you might be able to look at just like the even or odd terms, and it might be a simpler sequence that converges. And you'd say like, well, geez, if I looked at just the even terms of the sequence, that would be a subsequence where all the terms are just 1, a constant sequence. Constant sequences trivially converge. But the odd terms have a subsequence that are -1, that converges to -1. Well, that kind of observation typically leads to how you prove a sequence diverges. Is that you say, well, are there some sort of subsequences? Is there some sort of trend that are in the subsequences of this, that some other terms that they maybe go to some values that have a distance apart from each other? And if I kind of split the distance between them, then that's an epsilon that can work for me showing divergence. If that doesn't make a whole lot of sense, don't worry about it. We'll talk about subsequences in a future lecture, but let me just address this problem right here. Let's just get into this without thinking about subsequences, but thinking about the behavior of the sequence as even and odd terms. They are a distance of 2 apart. If we choose epsilon to be half this distance, then the absolute value of Sn minus S is going to be greater than or equal to epsilon for an infinite number of n. In other words, an infinite number of terms will be greater than or equal to 1, epsilon being half of 2, 1, no matter what value of S I pick. And you can say, why? How do I know that if I'm choosing epsilon to be half the distance? Why is that going to work? Think about any number S that you might pick as a limit. And when you say in convergence that absolute value of Sn minus S is less than epsilon, remember the graph we had above, it defined an interval on the vertical axis of S minus epsilon to S plus epsilon that was open. That interval had a length of 2 epsilon. All right. So if we know that there's basically terms, there's some epsilon to where terms on the sequence are here and here, then we have that the terms are an epsilon distance away from S, right? No matter what S value, I guess, we pick. So let's formalize that here. In the proof, we know we have to have 5 steps. And you'll notice I had to split steps 4 and 5 into 2 parts because I had 2 cases based on what happens in step 1. Step 1 is I say, consider any S and R. You could also write just let S be a real number, right? Pick a real number, any real number. I don't care. There's really no conditions on S other than it has to be a real number. You could write it in either way. All right. The second step, there exists an epsilon. This is where the work is. Through our scratch work, we say, you know what? I can pick epsilon to be 1. So choose epsilon to be 1. So set epsilon equal to 1. You could also write choose epsilon equal 1. All right. That's another way to write that. Now, I have to say for every capital N. All right. So let capital N be any index from the sequence. There's my step 3. Now I'm on to my steps 4 and 5. Right? We go back to this negation. I have to explain how there exists a little n greater than or equal to whatever n. You picked any index you want. Maybe you went out you picked capital N to be 1 billion. You said, I'm going to ignore the first billion in terms in my sequence. And now I'm going to say, what happens after the billionth term? I have to pick a little n greater than or equal to capital N. So I say, okay, well, here's what I do. I'm going to choose my little n based on whether or not that S was positive, or I should say non-negative, or negative. All right. So it could be either greater than or equal to 0 or less than 0. And which one it is going to help me determine how I choose my little n to be greater than or equal to capital N. And I do it as follows. In the first case, right, which I could label these cases in any order I wanted, but I take the first case to be S greater than or equal to 0. If that was the case from step 1, if you happen to have picked a non-negative real number, then I will choose my little n to be greater than or equal to capital N to be odd. It'll be an odd integer. Then what does that mean? Well, as I show here, that means that the distance between that term and this number that's greater than or equal to 0 has to be greater than or equal to 1, which is my epsilon. So I call that step 4a, and the conclusion I got was 5a. Right? Because I labeled it as 4a and 5a instead of 4 and 5, because that's only addressing half of my cases, right? Case 1. Case 2, this number S that you picked back in step 1 was negative. It was less than 0. Well, now I'll choose my little n to be even. And I know that there's even numbers as large as I need them to be. So I'll choose the even number to be greater than or equal to capital N. So this is step 4b. This is for the second case. And then my conclusion follows similarly as before. My distance between that number, the sequence, that term in the sequence in S is again greater than, in this case, strictly greater than the epsilon. I only needed greater than or equal. So that's 5b. Taken together, I have my steps 4 and step 5. I've completed the proof. I just had to split up the parts of the argument across two possible cases. So that's a basic idea between proving something like the sequence negative 1 over n diverges. Now, here are some other definitions, just kind of, we'll end the lecture with a little bit of notation and two definitions about divergence where limits exist, but we don't say that the sequence converges. We say it diverges to this limit. So we say a sequence Sn diverges to positive infinity if for every capital M strictly greater than 0, there's always some number capital N such that if I take all the terms, right? So there exists N. So maybe I'll label these for every M greater than 0. So there's step 1. Here's my step 2 in the proof. If I take all the little n's greater than or equal to capital N, there's my third step. That's going to have to be my proof. The conclusion is that Sn is greater than M. All right. And then we write the limit of Sn is equal to positive infinity, or we'll write something like Sn to positive infinity. But you need to read this notation. This notation right here does not mean convergence. We do not say Sn converges to positive infinity. That is wrong. If you write that, you should expect to miss a lot of points. That means Sn diverges to positive infinity, and it means this definition. It means that no matter how big of a number M is, positive in capital M, like I could choose a trillion, there is some point in the sequence after which all the terms, that's what steps 3 and 4 say, are greater than that capital M. And you say, okay, well, instead of a trillion, I'll choose a trillion squared. I'll choose a trillion to the trillionth power. Okay, there's some term in the sequence, if it's a divergence to positive infinity, such that after that point in the sequence, all the terms are strictly greater than that trillion to the trillionth power. All right, that's what this means for divergence. And there's a similar definition for divergence to negative infinity, which I will not write. And again, understand that it means divergence. Here's a proof of a very simple example. I labeled the steps. Prove that n squared diverges to positive infinity. Sometimes I don't write the plus. If I just have infinity, no, it's positive infinity. So my first step, kind of bring this on the same screen. For every m greater than 0, that means pick an m, any m that's greater than 0. Let m be greater than 0. And it's pretty easy to see how I would choose capital N in this case. I choose capital N because I have to have that there exists a capital N that's greater than the square root of capital M. And then I just let little n be greater than or equal to capital N, because my third step is, hey, for every little n greater than or equal to capital N, so I pick a little n, any n, as long as it's greater than or equal to capital N. Formally, we write let little n be greater than or equal to capital N. And then our conclusion follows, step 4. We just do the algebra. Pretty simple proof that n squared diverges to positive infinity. So, concluding remarks. When discussing limits of a sequence Sn, there are only 3 possibilities. The limit exists as a real number if and only if, this both ways, this right here, that means if and only if, okay? If and only if the sequence Sn converges. So if the sequence Sn converges, that means the limit exists as a real number. If the limit of the sequence exists as a real number, the sequence converges, right? It's the only thing that means. But the limit could also exist, but be the symbol plus or minus infinity. That occurs if and only if the sequence Sn diverges to positive or negative infinity, respectively. And then if we say the limit does not exist, we say that's true if and only if Sn diverges, but not to plus infinity or negative infinity. I'll add that in there in red. That's what I mean. If we just say divergent, but we don't mean divergent to plus or minus infinity, then you can safely assume that that's what I mean. If I just say, hey, it diverges. Otherwise, we'll generally specify rather specifically divergent to positive or negative infinity, because even though it's a divergent sequence, it has some trend to it that typical divergent sequences don't. So that's it. That's the end of this lecture. Thanks for listening, and I'll be talking to you in a future recorded lecture.